thanks for the introduction. It's quite a mouthful of a title, but we're going to jump straight into a code example to sort of motivate the problems we're trying to solve here. So here we can see a simple program that is just a map implementation using an array in the background. And here on line 5, we have an allocation of the key that needs to be boxed before it's inserted into the array. And on line 6 to 9, we just loop through the array, check if the key is already existing in the map. If it's not existing, then we actually physically put the boxed into the array. So after quick inspection, you can see that, it doesn't make sense to have this allocation here on line 5, and it should be moved down to line 11 so that only in the scenario in which the key has not been seen before should be allocated, right? The question is, how do we get from point A to point B, from the left side to the right side? And traditionally, the answer to this question is escape analysis. So escape analysis answers the question, does this object escape into, or does this object escape the procedure? And then the object can escape either by being passed to another procedure or being assigned to a field of another escaping object. And for this specific example, it's clear that escape analysis itself is not powerful enough to perform the optimization we saw at the beginning. So what we need is, since the object escapes on line 8 here, what we need is partial escape analysis. So partial escape analysis tries to answer the question, on which path or on which control flow path does this object escape the procedure? And here we have two different answers, right? So on path number 5, if we return inside the loop, the object does not escape. But if we return from line number 8, the object, or return from line number 9, the object does escape, and we need to materialize this object. And we generally, when an object has not escaped yet, we refer to it as being virtual. So this is a virtual object up until the point it's written to the array, and there it has to be materialized, and the transition from the virtual state to the materialized state is what we call a materialization, right? In the IR, this looks something like this. This is generally computed with some sort of static control flow sensitive analysis. At the beginning, we start off with an empty state. Once we handle the allocation, we have a new state for the object for the object boxed, which is virtual. And from here, we sort of go through the motions of static analysis, and we can see if we take the left branch, i.e. the return from inside the loop, we can keep the object virtual. However, if we go through the right branch and the key has not been seen before, and the store node here materializes this boxed object. So from this point forward, the state of the boxed object will be materialized. So after we run this analysis, we have enough information to actually get the code in this state that we would like to have. And generally, more abstractly speaking, the benefit of keeping an object virtual is that we can perform scalar replacement, i.e. that means we can replace all the fields of an object with local variables. And in practice, this means we have register writes and reads instead of memory reads and writes, right? So this is all like fine and dandy, right? Good, problem solved. The problem comes when we have a more complex example. So in the real world, maybe we have a list map implementation that is generic, right, on the key. Now, there is nothing for partial escape analysis to even do. There's no allocation in this put function. And this nicely illustrates what is the limitation of this partial escape analysis. And that is the fact that whenever we hit procedure boundaries, we're stuck, right? We have to say that the object escapes. For this, typically we solve this by inlining. So to get to the same end state that we had before, we would have to inline this put method into this client function on the right. And we can see the reason for this is because the allocation, this new integer, is on line 2 in the client function. And one problem that we're trying to solve is the fact that all prior work generally uses, or that they generally throw away control flow sensitivity if they perform any type of interprocedural escape analysis. So a previous algorithm would ask the question, does the parameter key escape the put procedure? The answer is yes, it escapes on line 8. And therefore, it would conclude that there is no benefit in inlining, there's nothing we can do. However, this does not really reflect what actually happens, as we just saw, right? If we inline put, then we can reduce, or then we can at least partially eliminate the object allocation. So this leads us to the research question or problem statement number one, which is how do we perform this partial escape analysis interprocedurally while also preserving control flow sensitivity when crossing method boundaries. Now, even if we have this information, even if we know where everything gets materialized, where objects are partially eliminated, it's still not a trivial question to answer whether or not inlining this is even worth it. So, whether or not inlining is worth it depends on, okay, how often do we even reach line number 7? How often do we see a key that has never been inserted before? Depending on this frequency, the benefit of inlining changes a lot, right? And even more so if the client itself is not a hot piece of code, really there's not too much benefit to gain from inlining it. And then there's a ton of other considerations with inlining, right? Code size, maybe if we have a specific inlining budget, maybe it makes sense to use this inlining budget in an area of code where that is more performance critical than this. Who knows? These are all really hard things to say. This leads us to or actually, before we go to that, I want to hammer this point down with some more data, which is if we take some sort of baseline algorithm that aggressively inlines every time an allocation can be eliminated. So here we only partially eliminate an object if we inline. Let's say we have an algorithm that inlines every time an object can be completely removed. We still have really inconsistent performance results. So you can clearly see like a benchmark like Factory benefits from this reduction in object allocations. But on the other hand, we also have benchmarks that get hurt by the potentially over inlining. For example, Scalap. If we break down the numbers, we see that the analysis phase works. We reduce the number of runtime allocations, but we have a larger code size, which leads to larger instruction cache miss rates, and which is all part of the reason that Scalap is now slower than it was before we performed this inlining. So really, here in this scenario, eliminating an object allocation just did not outweigh the inlining overhead, maybe, right? So this leads us to our second research question that we want to answer, which is how do we integrate this knowledge that we got from an interprocedural partial escape analysis into some sort of holistic cost-benefit model so we can make the most informed inlining decisions based on object allocations. The key insight and contribution of our work is the fact that we inject the virtual state. So we run the partial escape analysis intraprocedurally, but then inject the virtual state into the callee, where we run on another instance of an intraprocedural partial escape analysis, and then keep track of where these materializations would occur if we inlined put into client, for example. And then based on this information, combined with collected profiling information with like branch frequencies and stuff like this, we compute a materialization frequency reduction. So essentially, this computes how many runtime object allocations can we reduce by inlining this function. And based on this, we quantify the benefit and integrate this into an existing cost-benefit model. To give you a little bit more flavor of how the algorithm actually works, is generally speaking, we built it on top of some generic cost-based inlining algorithm that builds a call tree representation of the procedures. So in this scenario, every subgraph node corresponds to a single procedure in the call tree. And each subgraph node has an assigned cost-benefit tuple that takes into account various things, like graph size, call side frequency. It performs some inlining trials with constant folding, strength reduction, and more. So a lot of stuff is being considered for this cost-benefit tuple. And our goal is to run this an interprocedural partial escape analysis phase on a subtree of this call tree, compute this mapping between allocations and materializations, and from there, then compute the materialization frequency. So to give a maybe some intuition behind how this injection of the virtual state works and how it's run on an actual call tree is, generally speaking, the partial escape analysis will start at the root method. In this case, a root method has one allocated object here. After the allocated object, we have the virtual state of the allocated object. It hasn't escaped yet. But now we hit an invoke. And instead of treating this invoke as an escape, we treat it as an injection of virtual state and essentially spin up a new instance of a partial escape phase. And from this partial escape phase, we already have this bookkeeping information from the parameter type. And here, critically, or at least in this example, on the left branch, there is nothing causing this parameter to escape. But on the right branch, we escape the store field node, or the store field node causes the parameter to escape. And now what we can do is store, or we can create a mapping between this allocated object in the root method to what triggers the materialization in the subgraph node, in the callee of the root method. And now, based on this, we compute the relative frequencies. So here, if you can see in the subgraph 0 node, for example, if we have the allocated object here, and we have two materializations in subgraph 1 and 2, then we can compute the relative frequencies of all of these materializations. And then based on this, we can apply a boost function to this entire subtree in which we virtually injected the state. Now, yeah, this is just boosting the function. So how does our augmented inlining phase actually perform? Before I show you some benchmarks, I'll give you a brief inlining system overview. So all of this is benchmarked on GraalVM Native Image, so the ahead of time compiled Java compiler. And we ran it with 4 different configurations. So one is just base, that is just running the cost benefit based inlining. We have PESI, is our name for the very aggressive. We inline an object every time we can eliminate an object. That is run completely separately from the cost-based inlining. And then we have our augmented cost-based inlining algorithm with IPEA. And IPEA opt is just our algorithm has some hyperparameters that, like for example, how much do we boost the materialization? And for IPA opt, we just chose the most or the best performing hyperparameters for each individual benchmark. And this should just show an upper bound for how much performance we can get with our algorithm in this scenario. But the benchmark we should focus on is IPA itself. So here, this is a lot of information. We don't have to go through everything. I just want to give you the overall runtime improvements of our algorithm. So on average, geometric mean, the improvement is like 1.8%. However, there are a lot of benchmarks that don't respond very strongly to eliminating objects or eliminating object allocations or just in general inlining. So in this case, we have a few benchmarks that actually react very strongly to our optimizations from the Renaissance benchmark suite and Scala and Scala Dacapo. So here we have one. The maximum increase we got was about 24.6%, and around 6 benchmarks reacted fairly strongly with above 5% improvement. I sort of mentioned that we have various hyperparameters. I don't have time in detail to explain what they are and how they work, but essentially we spent a lot of time tuning these hyperparameters. And as you can see, right, for example, this benchmark on the right here, Kiyama, there's a lot more potential. Like if we have better hyperparameters, we can even get so there is a better inlining schedule in that sense out there for Kiyama, and we can reach this by choosing the correct hyperparameters. However, it's hard to sort of balance these hyperparameters across the entire bench suite, right? But this is just to give you an idea of the time we spent tuning the heuristics and how much maybe potential improvement there is still to be gained from these types of algorithms. Another thing we benchmarked was how many allocations are performed at runtime. So in this case, I just want to highlight a few, like Finagle Chirper. Here we clearly see, right, we have a reduction in runtime object allocations and consequently, we also have a reduction in runtime. So we have a speed up. The code runs faster. So here, it seems to suggest that due to us introducing control flow sensitivity across method boundaries, we get faster performance. Similarly with mnemonics. On the other hand, we also have a different example where we inline or we reduce the number of allocations less than with a more aggressive inliner, but it seems we make more accurate inlining choices, since even though we allocate a lot more at runtime, we still have a faster runtime performance overall. So it seems we sort of fixed a little bit of code bloat issues or over inlining issues in some scenarios. And yeah, these are the total. Interestingly, in total, we allocate more objects than we do with PESI, but we still have an overall runtime improvement with the geometric mean. We also, I'm gonna more or less gloss over these, but these slides are to show that we also have lower code size with this versus PESI and lower build times in total versus PESI, by not a huge amount, but a decent chunk faster. In conclusion, what I really want to drive home is how we solved preserving control flow sensitivity with these materialization mapping plus branch probabilities from profiling to compute materialization frequency, and how we integrated the benefit that we got from IPEA into the holistic cost benefit model. And here we use the materialization frequency as the main parameter on how much we boost specific subtrees, right? As sort of, I think one of the what we learned while working on this is that, well, we're only also seeing part of the picture again, in the sense that all we care about in this algorithm is how often an object gets allocated at runtime, and this ignores a lot of the other stuff. Like, okay, maybe an object is, we can push back the materialization of an object, and then we have lots and lots of reads and writes to a virtual object instead of a materialized object. This already can cause a speed up, right? And this we sort of ignore. And also, whenever we take a lock on a virtual object, we can eliminate this already in the intermediate representation. So we don't ever have to even go for the lock, because we know if an object is still virtual, no other thread or anything else can really have access to this object. And there we have no way of modeling the benefit that we get by keeping something virtual that has high lock contention, for example. And I think this would require a different type of algorithm to fully analyze something like this. Another thing that you could further improve on this is the fact that essentially we just simulate what happens if we inline and perform partial escape analysis. However, a lot of other optimizations also help out partial escape analysis, like code duplication. And it would be interesting to fuse more of these optimizations together, see what happens, see what is the potential for optimizations, and then make decisions based on this information. And last but not least, we implemented this on native image on ahead of time compiled Java. But the algorithm itself can easily also be implemented in the JIT compiler, and we have a nice framework there to easily modify how often IPEA gets run to reduce build times even further, or maybe running in a JIT compiler would require slight tuning of heuristics, but this would be a natural next step. And after this, I just want to say again, thanks to the VMIL' committee and organization, to the GraalVM team at Oracle Labs, my university that I also collaborated on this project, and both of my co-authors, of course, Theo and Alex. And with that, I should be perfectly on time and ready for questions. Thanks for listening.
Yeah, Jeremy. Actually, the mic is working, so you don't have to scream. Just do it.
So I need to
No, it's not supposed to be used.
just say something. Thank you. Hello. Thank you for an interesting talk. Can you hear me?
I can hear you, not too well, but I should be able to understand.
Okay. Um, I think you showed the performance was very much benchmark dependent, and
Yes.
your hyperparameters could be tuned for the different benchmarks. Do you
Yes.
think it would depend on the inputs a great deal as well? Like how much variance would you expect with ranges of inputs to those
S-
benchmarks?
By inputs, you mean like what sort of the type of um,
Yeah, the
inputs to the
workflow.
jobs, for example. Yeah.
Yeah, yeah,
Um,
yeah.
I think yes. I mean, so it's hard to say without like super analyzing the every specific type of benchmarks. But I mean, if you have right, if your branch probabilities change a lot based on the different inputs, then it could also affect the performance, right? Because if we build this materialization frequency, but we're the frequency calculations that we're making are based on like bad profiles, then yes, it could definitely we could make some suboptimal inlining decisions for sure. Definitely.
Right. Is that something you've looked at or not yet?
It's something. I mean, it's not something we specifically looked at, but I think it's also, in some sense, it's almost an orth. I mean, it's an orthogonal problem in the sense that there you sort of start going more in the direction of okay, how do we correctly profile applications? Whose responsibility is that? Is that the compiler's responsibility, or is it the people who try to deploy this code somewhere? Um, I don't know. I don't know what the current status is on this. Um, but maybe it would make sense to automatically update this if you have um, newly collected profiles, or if you have fresher profiling information. I don't know. Does that make sense to you?
Thanks. Yeah.
Perfect. Thank you.
Do we have another question? Yeah.
Sure. Can you hear me? This is Manas Thakur from Indian Institute of Technology.
Hi.
Yeah, so nice talk. We in fact have been working on some similar optimizations related to
Mm-hmm.
object allocation and deallocation for OpenGenine and could resonate to some of your
Mm-hmm.
insights as well, like for Renaissance benchmarks particularly and so on. I had one question. So you mentioned you would like to take it to the JIT compiler instead of the native image, and the previous question was about whether it's on runtime inputs. So what's the reason? I mean, is it because you feel there is a high variability with respect to the runtime if you do it statically or IoT, or is there any other reason you want to get to the JIT compiler? Is there any disadvantage of doing it over the native image compiler?
So let me rephrase the question just to make the audio quality isn't super high. So you're asking me whether or not the JIT compiler or migrating to the JIT compiler is, or what is the difference between the native image and the JIT compiler exactly? Did I
Yeah,
understand that correctly?
yeah, partly
Um,
that question.
yeah. So initially we decided to work on only the native image stuff because the JIT compiler is a lot more how do you say, sensitive to like long build times, and partial escape analysis is pretty expensive, especially once you go through multiple, if you have some code with multiple loops, and we run it quite a bit. So the call tree gets explored incrementally, and it runs it all the time, but only on a subset. But it actually turns out, I have another slide to this in the appendix, that it was, if you throttle it correctly, it does not actually spend too much more time in IPA than it would otherwise. But that was our primary concern. Regarding the performance, I do not really know. I don't know what changes in terms of the how you should change other hyperparameters to get better performance. this was something I would have to test out. I would suspect one thing that is advantageous, of course, is that if you're running it in the JIT compiler, you will have better branch probabilities most likely. So I could see it being even more effective if you have more, like if you get better profiling information in a JIT compiler versus native image and running PGO. Does that make sense to you?
Yeah, thanks. So I mean, maybe you would have to integrate those profiling characteristics with the inlining analysis, inlining-benefit analysis as well.
Yeah. Yeah.
Okay, thanks for the discussion.
Thanks a lot.
One more question is coming.
Mm-hmm.
Hi, Matthew. This is Michael speaking. I'm working at Dacapo. Could you maybe go back to the introductory example where you did the Scala replacement?
Here.
Right.
Or
Yeah, no, that's totally fine. I was wondering, since you look through the list at the call on line 4, where you call equals, basically, if you do the Scala replacement and use unboxed in there, wouldn't you introduce boxing on 4 as well? Or when in the pipeline is that phase run?
sorry, can you repeat the last part again? When is the
Yeah. I was wondering if you wouldn't introduce boxing as well on line 4. So
yes. Actually, I mean, so I'm doing a little bit of abuse of, so I've just sort of glossed over this equals, but theoretically you would also inline equals, but I just didn't want to do that in this situation because almost any compiler will always trivially inline this equals function. But here it's because we took this code from somewhere that we found on GitHub. But to your second question, the scalar replacement gets done during the partial escape analysis phase. So really this is a simplified a virtual state, but the virtual state actually contains the fields of all the objects. So while we run escape analysis, we can sort of save the effects, and as soon as a fixed point is reached, we apply all the effects into the IR, and then immediately all the scalar replacement would happen. But here, in that sense, we wouldn't perform scalar replacement. We would only perform it after we inlined equals as well, as far as I'm aware. Does that answer your question?
Yeah, thanks. Follow up on that, because if I remember correctly, list was a type of object, an array of objects. So you would also like already specialize for the type and like know that list is an array of integers. Then specialize.
Yes. Yes. So usually there you would put like a speculative optimization step into it, because you know that, I mean, this is sort of out of the scope of this analysis phase, but since we also sort of collect like type information, so we know that list is always an integer, or we don't know that it's always, but we have a high probability that the object inside list is an integer, so we put a guarded optimization step there, some sort of speculative optimization step. Yeah, exactly.
Okay, thank you.
Perfect. Thanks for the question.
Any last question? Then let's thank Matthew again. Thank you, Matthew.
Thanks, guys.